Calculating the pH of a strong acid or a strong base is really easy. And this is the only type of pH calculation for the SL class. HL class should also be comfortable doing this quickly, especially for paper 1. The reason why it's easy is that we are going to always assume that strong acids and strong bases ionize completely or dissociate completely in solution. And we represent that with a forward arrow. So the acid completely splits apart into H plus and Cl minus. So we don't consider there to be any HCl's left. There's only H pluses and Cl minuses. So it's not an equilibrium scenario. We consider this just a forward reaction that goes to completion. In HL, we would look at ICE or ICE calculations when things are equilibrium, so that's why I've set it up this way. But the SL class should be able to follow too. If we start off with a 0.1 molar HCl, when it dissociates, we think of all of the HCl going away. So eventually there's zero concentration of HCl once we've established equilibrium or once the reaction is complete. And once we've done that, then these will both now have a concentration of 0.1 mole per dm cubed, because for every one HCl, we made one H plus and one Cl minus. It's a 1-to-1-to-1 ratio. So notice that the starting concentration of HCl is now the actual concentration of H plus in the solution. Okay, so that's what I point out down below. The HCl concentration is equal to the H plus concentration. So as soon as we know the HCl concentration, we actually know the H plus concentration. And if we know that, we can calculate the pH, because pH is negative log base 10 of our hydrogen ion concentration, negative log base 10 of H plus. So you can also just see it if this is 0.1, if it's an easy number, like for paper 1, if we have 0.1, you should be able to convert that into an exponential so that you can really quickly say, well, 10 to the minus 1, that means pH 1. So all these relationships between H plus and pH, you should be quite comfortable converting between them. If it's a simple number, you can turn it right into a pH value. So once we know the acid concentration or the base concentration, then we immediately know the H plus or the OH minus concentration, and we can get the pH value. Now, with the bases, it just adds one extra step, and we'll do that here. If we had the same thing for NaOH, if I had 0.1 mole per dm cubed NaOH, that would mean when it dissociates, I have 0.1 mole per dm cubed OH. So this is just adding one extra step to our pH calculations, or maybe it's two extra steps. We can count afterwards. So this is the first part. This is the part to know that whatever the concentration of the strong acid or base is, that's the same as the concentration of the important ion, the H plus or the OH minus, because they fully dissociate in solution. Well, 10 or 0.1 molar is the same as 10 to the minus 1 molar, and that means a p-value of 1, because whatever the negative exponent is, that's what the p-value is. The only thing is right now we're dealing with POH. So when the concentration is 10 to the minus 1, the POH value is 1, and now we can figure out that the pH is 13, because POH and pH have to add up to 14. So the only thing that's different about a strong base calculation is that you have to do the added step, and remember that what you can figure out is POH from hydroxide concentration, and then the POH and the pH have to add up to 14. Okay. So we can do other examples. It's all the same. 0.1 molar means 0.1 molar H plus. That means pH 1. Nitric acid, 0.001. That's the same as 10 to the minus 3. So 10 to the minus 3 is pH 3. Here's an NaOH example. This is 0.01 molar NaOH. So that's going to be like 10 to the minus 2. 10 to the minus 2. Now this, I set it up slightly different. You could first get POH. The POH would be 2. That would lead you to a pH of 12. You can also immediately figure out the H plus concentration, because the OH minus and the H plus concentration always have to multiply together to 10 to the minus 14. So if you know OH minus is 10 to the minus 2, H plus must be 10 to the minus 12. Therefore, pH is 12. The only way that this gets at all slightly tricky is when you deal with diprotic bases or acids. So like sulfuric acid is the classic acid that you deal with that's diprotic. And you'll notice, especially on paper 1, they often give you the acid concentration of sulfuric acid as a half, as a 5 value. And that's because when it fully dissociates, it splits apart into 2 H pluses for every 1 acid molecule. So although the concentration of H2SO4 is 0.05, when it dissociates, it has an H plus concentration of 0.1, twice as big. And so now 0.1 is 10 to the minus 1 is pH1. So with diprotic acids, you just have to watch that and know that that ratio, right, is what 1 acid equals 2 H plus for diprotic acids. And this would be 1 base equals 2 OH minus for diprotic bases. And the only real examples of this you guys have to be aware of, although I suppose they could come up with others, is H2SO4 for acid, sulfuric acid, and barium hydroxide for bases. So recognizing that these diprotic exist and just knowing how that's going to affect those ratios is the one thing to watch for. Otherwise, doing calculations with strong bases, strong acids should be fairly simple.